Good day, everyone. This is Dr. Mansour Al-Matarne from the University of Jordan. And this lecture, I will be talking about the Schrödinger equation and the Hamiltonian. As you see in this equation, this is what we called Schrödinger equation, non-relativistic, time-independent, linear second-order differential equation, where h here, h hat, represent the Hamiltonian, and psi is the wave function to produce, and this operator acts over the psi to produce the eigenvalue, which is the energy here, and produce once again the psi, the same wave function. This Schrödinger equation can be written actually in terms of electronic coordinates and the nuclear coordinates, the lowercase and uppercase. So the Hamiltonian here, the h hat, contains the operators associated with the the kinetic energy and the potential energy. So simply, it is associated with each measurable parameter in physical system. And the operator actually associated with the system energy, it's called the Hamiltonian. Now, this equation needs to be solved. So the assumption here of the product form of the wave function should be really applied here. Right? So we have to separate the variable. So the psi r small letter r capital letter should equal psi r lowercase times psi r uppercase. So simply, and that's what we called Hartree product. And I will be talking about this in another lecture later on. I will focus here on the Hamiltonian, which is equal electronic Hamiltonian plus the nuclear Hamiltonian. As you see here, the first term represents the kinetic energy and the second term represents the potential energy. And the kinetic energy, which is equal in classical mechanics half mv square, where the momentum equal the mv. So if we write v square equal b square over m square and rewrite and rearrange the equation, we will end up with p square over 2m. And in quantum mechanics, momentum is an operator, can be written as h bar over I, the first derivative with respect to x, for example. And the b square will be minus h bar square d square over dx square. Now, how we write the Hamiltonian for any system? So, for example, if I have the atomic Hamiltonian, as you see here, we have one nucleus and two electrons, electron I and electron J. So here we have attractive forces between the first electron I with A, with the nucleus A, and also we have attractive forces between electron J with A, and also a repulsion between these two electrons Rij. Right? Now, how we write the Hamiltonian for this system? The Hamiltonian actually contains three major terms. The first one will be the kinetic energy and also the potential. And here we have two kinds of potential. We have the attractive forces between electron and nucleus, and also we have the repulsion between electron, right? So that's like the general terms. So these three terms represented by this equation. Now, to get a clear picture, these three terms can be split into five terms. So when we deal with the kinetic terms, here we have the kinetic energy for electrons and also the kinetic energy for the nucleus, right? So two kinetic energy for both electrons and nuclei. The second term here, we have the potential of a nucleus with electrons, and also we have the potential of electron-electron repulsion. And the last term here, the potential between n and n nuclei, between the nucleus A with the nucleus B. So simply, the Hamiltonian always should contain these five terms. And again, the sum of these five terms represent the electronic Hamiltonian and also the nuclear Hamiltonian. This symbol del square called Laplacian operator, which is equal the second derivative with respect to x and y and z square, as you see it, and this is in Cartesian coordinates. So these 5 terms again, it will be given by this equation. The first term here represents the kinetic energy for the electron, where you have here some constants. The first term in kinetic energy, here we have h squared over 4 pi square me, the mass of electrons, and really represented by the reduced mass, where we end up with the mass of electron. And also we have the summation, again, too, when we deal with a case where we have 2 n electrons and m nuclei. And also we have another constant, e squared over 4 pi epsilon naught, the permittivity of a free space. And again, this actually comes again from the classical Coulomb potential, right? So we have here the potential and energy between a nucleus and electron, and here we have the potential between the 2 electrons, and here we have the kinetic energy of the nuclei, and also the last term is the repulsion or the potential between nuclei as well. So 5 terms represented by this equation as a summary. The first term represents the kinetic energy for electrons. Second term represents the potential energy between electrons and the nuclei. So here we have 2 summation. The first one represents the number of electrons. So for example, if I have J equal 1 for electron number 1 over summation of nuclei, so simply I will deal with electron number 1 with the nucleus A, electron number 1 with the nucleus B, with C and D, and so on. When I finish the number of nuclei, then I go to the number of electron, the second one, so J will equal 2, and 2 with A, 2 with B, 2 with C, and so on. Now the third term represents the electron-electron repulsion between 2 electrons, I and J. And this is really the most difficult part in solving Schrödinger equation, and that's what we call the two electron integral. This is the most difficult term we do calculate trying to solve Schrödinger equation. Now the fourth term, it's the kinetic energy for nuclei. Again, here we have to include the mass multiplied with this constant, and the last term represent the potential energy between the nuclei, ZA, ZB, over the distance RAB. Now to make things really simple, and because we always like to simplify things, so if we choose units such that h bar equal 1, e squared over 4 pi epsilon naught equal 1, and that's the atomic unit, and the reduced mass equal mass of electron, again because the mass of n, this is really massive compared to the mass of electron. So if we neglect x value, this will be cancelled with this, so we'll end up with mass of electron, and this is equal 1. So and if we do that, and keep in mind like the energy will be here in Hartrees. That's the new unit in atomic units. We call it Hartrees. And 1 Hartree equals 4.35 10 to minus 18 joule, and 1 Bohr equal this number of 10 to minus 11 meter. So if we do and apply these new units, we will end up with this equation for the 5 terms. This equation can be divided into 2 terms really. The first one, as you see here, the 3 terms represent the electronic Hamiltonian, and the last 2 terms represent the nuclear Hamiltonian. As you see, the kinetic of nuclei and the potential of nuclei. According to Born-Oppenheimer approximation, which is the approximate separation of variable, we assume 2 things here. The first assumption is the nuclei are held fixed. Simply, this term equals 0. Why? Because the nucleus is almost like 1848 times heavier than an electron. For the second assumption, we assume that the potential energy for a nuclei is constant. And this term, it will be really added at the end of our calculations. The last term is really easy to calculate according to Coulomb potential. So this is really can be added at the end. So when we calculate the total energy, it will be equal the electronic energy plus the V and N. So it will be added at the end. So the kinetic energy for nuclei is zero, and the potential energy of a nuclei is constant. So according to Born-Oppenheimer, then this equation can be written as three terms. So we neglected two terms. So here the Hamiltonian will be the electronic Hamiltonian. In the last slide here, we have an example of writing Hamiltonian for H2 molecule. As you see here, we have two nuclei with two electrons. Again, we have different attractive forces and repulsions between these electrons and the nuclei. And again, that total Hamiltonian, it needs to be written in 5 terms. So again, I will leave this question for you guys to write, and your answer should contain 10 terms. So try to do this. And again, I will explain this question actually in my second lecture about Hamiltonian. Thank you very much for listening and have a good day. Bye-bye.